Hi, this is Dr. Chris Burke. I'm here with another live stream of Advent of Code. This is for review for CSCE 155E and 155H. We're going to be doing everything here in C today. Second here. We're going to be doing Advent of Code Day 2. We did Day 1 yesterday in class, and today we're going to be doing Day 2. So let me go ahead and transition over there. All right, so I've not looked at it yet, so I don't know how long this is going to take me, but it's all right. We're going to be using this as a review for your final exam, here's the actual program for today. So on the way to your gravity assist around the moon, your ship's computer beeps angrily about the 1202 program alarm. On the radio, an elf is already explaining how to handle the situation. Don't worry, that's perfectly normal. And then the ship computer bursts into flames. You notice that the computer magic smoke seems to have escaped. The computer ran Encoding programs like the gravity assist program it was working on. Surely there are enough spare parts up there to build a new Encoding computer. An Encoding computer is a list of integers separated by commas, like 1, 0, 0, 3, 99. To run one, start by looking at the first integer called position 0. So obviously we're going to probably use some indices here as well, and so some arrays. This is an opcode, either 1, 2, or 99. The opcode indicates what to do. For example, 99 means that the program is finished and you should immediately halt. Encountering an unknown opcode means something went wrong. So, for example, 0 and 3 are probably going to be invalid. Opcode 1 adds together numbers read from two positions and stores the result in a third position. Okay? The three integers immediately after the opcode tell you these three positions. Okay, so these are not invalid opcodes. These are going to be used as position numbers. The first two indicate the positions from which you should read the input values, and the third indicates the position at which the output should be stored. For example, if your Encoding computer encounters 1, 10, 20, 30, it should read the values 10 and 20, because those are the direct next two, and add those values together to get 30, then overwrite the position at position 30 with their sum, which is going to be basically writing 30 again. Opcode 2 works exactly like Opcode 1, except it multiplies the two inputs instead of adding them. Again, the three integers after the opcode indicate where the inputs and outputs are, not their values. Okay. Once you're done processing an opcode, move to the next one by stepping forward 4 positions. So we're just going to add 4 to it. For example, suppose that you have the following program. For the purposes of illustration, here's the same code. Let me go ahead and increase the size for you at home here. Here's the same program split into multiple lines. So 1, 9, 10, 3. The first 4 integers, 1, so we're going to be adding these together, are at position 0, 1, 2, and 3. Together they represent the first opcode, 1 addition, and the positions of the two inputs, 9 and 10. So those and the position of the output, 3. To handle this opcode, you would first need to get the values of the input positions. 9 contains 20, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 30. And then 10 would be 40. So we're going to take 30 and 40, and we're going to add them together, and we get 70. Then store this value in the output position. Here it's 3, which is exactly where it starts, so it overwrites itself, just as it says here. Afterwards, the program looks like this. Okay. Step forward 4 positions. So from this initial position here, you're going to go 1, 2, 3, 4, and that gets us to the next opcode here. And that's going to be 2, so it multiplies whatever's at 3, which was 70 that we just wrote, 11, which was 50, and so 70 and 50, and we'll multiply those together to get 3,500. And then the last one here, this is 0, so it's going to go back to 0 and input 3,500 there. Stepping forward 4 more positions gets us back to 99, which at this point is halting the program because remember it's only 1, 2, and 99. Okay. All right, here are the initial and final stages of a few more small programs. So these are going to be our testing programs, test inputs that we're going to be using. Once you have a working computer, the first step is to restore the gravity to assist the program so that the 10202 program alarm and state it has just before the last computer caught fire. To do this, before running the program, replace position 1 with the value 12 and replace position 2 with the value 2. What value is left at position 0 after the program halts? Okay, so we're going to have to do this simulation of this computation, which is just going to involve one array. And then also we're going to probably have to take our input here and then last computer caught fire. To do this, before running the program, replace position 1 with value 12 and replace position 2 with value 2. What is left at position 0 after it's done? So let me go ahead and get my input here. Remember that those inputs are going to be different every single time, or they might potentially be different for every single user. So instead of doing this as a file I/O program, I'm just going to do this as a regular old array. And I'll call this, I'll call it my program. Right. And just to verify that I cut and pasted it correctly, we do have 0, 0 at the end here. So one very, very long line here. Now, I'm going to want to know how big this is. Remember, I'm using elision here by not specifying the size of this array. The compiler's smart enough to figure that out and do it for me. What I want to do is I want to make sure that I've got enough here. So let's do a character count here of how many commas there are. I'm not using any commas. There's one comma up here, but let's go ahead and do a character count. Let's see. All right, Adam is not doing a character count for me. So what I'm going to do is I'm just going to open it up into a well, here, I can do it right in my browser. So there are 120 commas, which tells me that there are actually 121 elements. Right? So I'm going to actually put that into a value here. That's my actual program that I'm going to want to actually run it on. But of course, I want to be testing this. So let me go ahead and grab this input right here. And this is what we're going to be using for testing. So I'll make sure that I've got the actual input here, and I'll put that off to the side. But in addition, I want however many elements there were in the the illustration program. And that's so there are 11 in there. I counted 11. 2, 4, 6, 8, 10, 11, 12. Sorry, 12. There we go. Now, since this is a review, remember that variable length arguments arrays are highly discouraged. You should not be doing this in practice because it allocates it on the stack. But these are small enough that it's not going to matter. Again, if you wanted to do this properly, you would use a call to malloc. But then, of course, you wouldn't be able to make this assignment immediately here. You'd have to go into a file I/O and read these out of a file or something and populate your array. So we've got our program here. Now what I want to do is I want to simulate that computation. So the simulation of the computation is going to start at the current index. So I'm going to need a current index. And I'm going to start at 0. Now I don't know how long this program is going to execute, so it's most appropriate to use a while loop here because I don't know how many iterations I'm going to go through. Maybe I'll even keep a counter of that, iterations. Right. And then I'll go ahead and increment that as I go through. So what I want to make sure is that the current index, whatever's stored at the program's current index, while that's not 99, then I will go one more iteration, because if it's 99, then I break out of this loop and I'm done. And what I ultimately want to report is the element, the value at the first index. So value at 0 is going to be %d and the line. That's what I want to report, right? Ultimately, 3500 is the final execution of this example program. Here's the final state of this one. Here's the final state of this one. If we wanted to be more sure, we could actually go ahead and print out everything. So let's go ahead and do that. Let's go ahead and print out the final state of the program. And to do that, it's just a simple for loop. For I equals 0, I is less than n, I plus plus. I won't go to the next line because I'll just print them all out on the same line. And then I will go to the next line down here. Okay? All right. So now what I need to do is actually simulate this program. Now to remind myself here, if the opcode is 1, then it adds the numbers together. If it's 2, then it multiplies the two numbers together. And again, it looks at the next one right over. So what I'll do is I'll go ahead and put those into two temporary values here. Well, yeah, if it's 99, then I'm out. So if it's 1 or 2, so let's go ahead and check those. If the current program's index, in other words, these are opcodes. If this is 1, then I'll be adding them together. Otherwise, if it's 2, then I'll be multiplying to get them together. And I do want to make sure that this is a valid program. So if there's anything else, remember it's an invalid opcode. So I'll go ahead and print an error message. What that opcode is. And then I'll go ahead and exit for now. Maybe we want to handle that a little bit differently later on, but that's good enough for now. All right, so if it's 1, then I'll go ahead and get the one next to it. That's 1 over. The one beyond that now, what you've got to realize here is I'm just getting the contents here. These are going to actually be indices, so maybe I should label them as such. Index of A and index of B, right? And then index of C is the third one over, okay? Now, once those are out, I actually need to get those values. So we could go ahead and declare a bunch more variables here, but I'll just go ahead and update the program directly. What I mean by that is I will go ahead and set index of C equal to program of index of A, and then opcode 1 corresponds to addition, so it'll be program of index of B. All right? And then I need to update my current index, and I'm going to go over by 4. Right? Now this is exactly the same thing here, except that instead of addition, it's going to be multiplication. Okay? Now you see a lot of redundant code here. Maybe it would be good to go ahead and pull this redundant code out and reduce the amount of redundant code here. And I'll go ahead and do that. It's going to be the same regardless. I was reluctant to do this at first, and then of course this is going to be common as well. Right? I was reluctant to do this at first because I have a feeling that in part 2 they're going to add more opcodes or something, and so if it could be that maybe there's an invalid program and we go beyond the size of the array and we have to detect that or something. And so I wanted to make sure that the opcode, that I was guaranteed that those elements would be there. So I was kind of reluctant to do this, but we'll go ahead and do this for now. Maybe we have to come back and change it and fix it later. But there we go. We've got that. Let me go ahead and compile this, see if I've got any errors. All right. Oops. All right. It's not going to let us do a VLA like that. There we go. It's just that I had to let the compiler figure out how many elements are in here. But of course, I still need that down below. All right. Let's go ahead and run this. And there's the final state. And the value at 30 is going to be 3,500. So at least we know that for that one test case, it works. Let me go ahead and make sure that the rest of it is also correct. The final state would have been, let's see, jumping forward here, 9, 10, 70, 2, 3, 11, 0, 99, and then of course the last three are untouched. That looks pretty good. So I'm pretty sure that it works for that small example. Let's go ahead and try it for another test case before we actually, commit to doing our answer. All right, and let's do this last test case here, which looks like it's the most substantial. That's 4. There are 9 things there. Let's go ahead and compile that again. Run it, and there's our expected final position of final value of 30. That agrees there. 1, 1, 4, 2. 5, 6, 0, 99. So I have a reasonably high confidence here that I've got a working program. I just have to understand what they mean by this. 1202 program state had just before the last computer caught fire. To do this before running the program, replace position 1 with the value 12 and replace position 2 with the value 2. And that's probably has something to do with the randomization and making it a little bit different or unique to each user. I think I already cut and pasted this. Yes, I did. It's still back over here. So let's go ahead and run this. But as it said in the instructions, I'm going to have to change a few things. So program, let me go back. Replace that at position 1 with the value 12 and 2 with 2. All right. There we go. There's the final state and the final number that looks like a random, weird enough number that it might be right. Let's go ahead and try it. And we got the right answer. All right. Great. So, good. The new computer seems to be working correctly. Keep it nearby during this mission. You'll probably use it again. So hint, we're probably going to use some of this code again. In fact, if you're going to be doing this day to day, you might want to go back and clean it up a little bit. In fact, you might want to modularize it and put it into some functions so that you can reuse it, anticipating that you might want to cut and paste it and use that code again or use that simulation again. Real Encode computers support many more features than your new one, but we'll let you know what they are as you need them. Right? So we're probably building some sort of a finite state machine or like a simplified assembly program language, which a lot of years past have done. However, your current priority should be to complete your gravity assist around the moon. For this mission to succeed, you should settle on some terminology for the parts that you've already built. Encode programs are given as a list of integers. These values are used as the initial state for a computer's memory. When you run an encode program, you make sure to start by initializing the memory to the program's values, which we already are. The position in memory is called an address. For example, the first value in the memory is at address 0, then 1, 2, etc. So an address is an index in this case. Opcodes like 1, 2, or 99 mark the beginning of an instruction. The values used immediately after an opcode, if any, are called the instruction's parameters. For example, the instruction 1, 2, 3, 4, 1 is the opcode, 2, 3, and 4 are the parameters. The instruction 99 contains only an opcode and has no parameters. Okay. To address the current instruction is called the instruction pointer. It starts at 0. After the instruction finishes, the instruction pointer increases by the number of values in the instruction. Okay. So for all of the ones that we just did, it had 1 opcode, 3 parameters, so it jumped past all of those by going to the next one 4 away. Until you okay. This is always 4. Oh, okay, so it's always going to be 4. Oh, for the add and multiply instructions. The alt instruction would increase the instruction pointer by 1, but it halts the program instead. With terminology out of the way, we're ready to proceed. To complete the gravity assist, you need to determine what pair of inputs produces the output, this. The inputs should still be provided to the program by providing the values at address 1 and 2, just like before. In this program, the values placed in the address 1 is called the noun, and in address 2 is called the verb. Each of the 2 input values will be between 0 and 99 inclusive. Okay. Once the program has halted, its output is available at address 0, also just like before. Each time you try to pair of inputs, make sure that you first reset the computer's memory to the values of the program, your puzzle input. In other words, don't reuse the memory from the previous attempt. Got that. Find the input noun and verb that caused the program to produce this value. And then the actual value that we give in this, we're going to have to multiply 100. Wait, no, this is a little bit different. Find the input noun and verb that causes the program to produce the output, this number. What is 100 times the noun plus verb? For example, okay, so we just need to find the noun and the verb. We can't simply find, okay. And then we need to manually probably multiply 100 by the noun plus the verb. Okay, I understand now. Basically what we're going to want to be doing is we just did one simulation with those values that they gave up at the front here of replace the value 1 with 12 and 2. So this is our noun before, and this is our verb. What we're going to want to do is we're going to want to simulate this over and over again for various values of the noun and the verb, 0 to 99, so at least we're given a bound here. So all this is going to be is 2 for loops for each noun, for each verb, and then we're going to want to simulate the program, check to see if it results in this number right here, and if it does, we'll just output the noun and the verb that gave us that value, of course multiply the first one and then plus this verb, and that's going to be our answer. So I was right in that we probably should have put this into a function because it will greatly simplify this. So I don't want to lose this, so let me go ahead and duplicate this. Because we know that this works, and if I screw anything up here on day 2, part B, I can always go back to part 1 and find the code that actually worked, that I know works. And you should be doing that, but you should be doing that with a version control system with Git. You should be checking this into Git, tagging it with works, making or at least making a local commit or something that you can always go back to if it screws up. And unfortunately, we're not given any more examples here, so I'm not going to be able to do any testing, so there's no reason to keep this stuff here. All right. And there's also, I was wrong. They're not going to make us do the number of iterations. Another common thing that they do would ask you, how many iterations does it take to reach this magic number or whatever? And that's why I put that in there, anticipating that, but I was wrong. So I'm going to take all of this code, and I'm going to put it into a function called simulate. And we're going to want to take a program, and we're also going to want to and I'm going to make the assumption here that they're not going to give us a bad program that is going to escape the bounds of the of however big it is. So let's just take an int star, and I called it program here, so I'll keep that. Okay. And we're making changes to this, so the calling function will be able to see what's stored at 0. And we'll also assume that it halts validly. And so what I'm going let me just do one simulation of this to show you what I'm talking about. So if we just call this function on simulate on the program, then this is as it was before, except for we of course need to change the thing at position. Let me create two variables here: int noun, and it was 12 before, and it was 2 for the verb, I believe. Let me double check that. So position at 1 is 12, and then the 2 at 2. And so what I would do here is, before I simulate it, I would want to make sure that I change the program's memory, or whatever they referred to it as, of 0 to noun, and programs of 2, I will change that to the verb. All right. Then I'll simulate the program and see the final state here. Okay. Let me go ahead and show you that this still works. All right. Oops. It's going to be a void function. It's just simulating it. But that's just a warning anyway. Okay, I must simulate. Okay, there. It was a misspelling. Sorry about that. All right. And when I run this, I think I get the same value as before, but let's double check that. Let's see, where's my answer? 4138687. 4138687. So here's a good term to learn. I've refactored my program before to make it a little bit more modular. In other words, I've not changed the behavior of the program. The program does exactly the same thing as it did before, but I've made it a little bit better in that it is now modular. And so what I can do now is I can go into another loop here, and instead of using these two hard-coded values, I can actually iterate over all the possible values. For int, instead of calling it I and j, I'll call it noun and verb. And remember, it said that it could go up to 99. So there's every single paired combination of values for noun and verb. And now what I can do is I can take this and put it into that loop, right? And once I've simulated it, I need to check, instead of blindly printing out the final state here, what I'll do is I will check to see if it is equal to this output value right here. So if programs of 0 is equal to this, then I will go ahead and print the noun and the verb that got me those things. But more importantly, I'll output the solution. The final value is going to be the noun times 100 plus the verb. All right. And then I don't need this stuff anymore. I'll just go ahead and comment it out for now. But remember, in actual production code, in actual code that you submit for grading and evaluation, you do not leave dead code in like this. I'm just leaving it here for now in case we want to come back to it. I don't want to lose it. Okay? Now we have found an invalid opcode. So instead of exiting, which is never a good idea, we'll go ahead and simply return. And because I put this into a function, now I can do some error handling here instead. Okay? I've got a lot of invalid opcodes. and no solution. So I do have a bug here somewhere. Oh, duh. I was saving that for later, but remember that that every time you simulate this program, it's going to actually change your array because we are passing this by reference, of course. We don't have a const here, and we don't want a const here because we will be making changes to this thing. But as it said in the write-up, that you need to restart the simulation for each new noun and each new verb as it was before, okay? As it was originally in our input over here. So what I want to take this opportunity to remind you that we could reset it, program equals to program. Well, that doesn't do anything, right? Even if we made what we want to do is we want to make a deep copy of this every time we call simulate on this. So what I'm going to do is I'm going to go ahead and write a function to do that. Right? So int star deep copy. Right? Good review here. I will make this one const int star array because I'm not going to be making changes to the array that you give me, and I'm making that promise that I'm not making changes to it. Instead, I'm going to be making a deep copy of it so that you can manipulate that copy and do whatever you want with it. In particular, what we're going to do is we're going to create a new copy, hand that off to the simulation, let the simulation run, and then we'll want to clean up after ourselves as well. So we also need to pass in the size of the array. Here's our copy. I'll just call it C. Make a call to malloc. Size of int, because this is an integer array and we want n of them. Right? And then I'm going to go into a for loop here for int I equals 0, I is less than n, I plus plus. Right? And a c sub I is equal to array sub I. Right? Now, if you do know C, it's going to be a lot better to use a memcpy, but when we didn't cover that in this course, and two, I want you to think algorithmically. That I want you to think of how this might work at a higher level. So we're not going to be using. You're free to use memcopy, of course, if you know what you're doing. But for now, I'm just going to use a regular old for loop here. We've made a deep copy. Now down here, what I'm going to do, instead of passing it program, I'm going to have a copy of the program. Right? And I want to make sure to do that first, actually, because we want to copy it and then set the noun and set the verb and then simulate the program. But we're going to be simulating the program on the copy, checking the copy of 0 sub I to see if it's equal. And then we repeat that process all over again. Okay? Now, one thing that you'll notice here is that we do have a memory leak, and we don't want this. Once we have the copy, we change its initial memory or whatever. We simulate that program, check to see if it's what we're looking for. If not, at this point, we're done with it. So we need to free the copy to make sure that we're not leaking memory. We couldn't have done it up here because that would have been before the simulation. We still need it. We couldn't even have done it after the simulation because we will be checking the first element. So what we need to do is we need to make sure that we're freeing it only after we're done with it. Okay? Oops. We also need to pass in the size of the array. All right. Let's run this again. Hey, great. We found a solution, 66 and 36. 66 times 100 is going to be 6,600, plus 36 is going to be 36. Again, we don't have a nice test case that they gave us that we can simulate this, but we can go ahead. But we're pretty sure that it's going to work because we simulated it for the first one, and that had several test cases. So cross your fingers with me and hope that it. Oh no, it's not the right answer. Your answer is too high. Okay. All right. So I will make a note of that here. Is too high. I probably forgot something. Let's see. So you just need to reread this. You've placed the value in address 1 is called the noun, and 2, I did that right, 1 and 2, good. Noun and verb. Each of them will be between 0 and 99 inclusive. Right? Verb, verb. Okay. Program has halted. The output is available at address 0, just like before. Each time you try a pair of inputs, make sure that you first reset the computer's memory to the values in the program. Yep, we still have that. And it's still 121. Yep. So it was 66 and 36. 6636. Let's see. Do we have anybody online? Hello from Brazil as well. But no, nobody else is watching, so nobody else is going to be able to help me with this. Oh, duh. There. What we were doing before, here, let me back it up. What we were doing, we were resetting these up here rather than the copy. And I just needed to make sure that I reset I get the deep copy of the program. In fact, I could have, if I really wanted to, I could make this into a const, and the compiler would have caught that for me. But otherwise, I'm making only changes to the copy. I'm only passing the copy, and I'm only checking the copy at this point. So unfortunately, because of that stupid bug, my record is now blemished, and it was only one viewer anyway. So let's see if it'll let me do this. Otherwise, generally, it throttles you and forces you to wait a minute or two. Maybe it even increases as you go along here. There, I finally got the right answer. I was only one off. Okay. So that is Advent of Code Day 2. Again, follow best practices. Unfortunately, I did not follow best practices where I was, basically copy pasting or using. Not modularizing it right away. I should have done that. Making it, testing. I did as much testing as was reasonably possible with this example, at least. But you might want to go back, especially if you're following along and you plan to go on with the rest of the Advent of Code. You might want to go back and modularize this and clean this up a little bit more, because I'm sure that if this is repeated on subsequent days, that you're probably going to want to reuse it, and you're going to want to make sure that it's good code so that it's reusable code. Okay. Thanks for joining me today with the Advent of Code Day 2. Again, it is December 10th. I'm doing these a week late because I'm using them as usual as a review for my CSCE 155E course. That's Computer Science 1 using the C programming language. And don't forget and if you're in that class, don't forget your your final next week. Otherwise, just have fun coding with the Advent of Code. Thanks.